Welcome to the Explainer. Today we're unpacking something that honestly feels like absolute magic, but is actually grounded in pure, fascinating science. Think about the everyday tech you use constantly, your smartphone, that tablet, or just the Wi-Fi router sitting in your living room right now. We stream videos, we fire off texts, we play games with friends across the globe, and we do the whole shebang without a single physical wire attaching our devices to the wall. So how is that actually possible? Well, it relies entirely on this invisible world of physical science. Specifically, today we're going to explore the core concepts of Grade 7 Physical Science Unit 04, Lesson 6, focusing on the electromagnetic spectrum and its real-world technology applications. We're going to decode the invisible rules that govern our modern lives. Okay, let's dive into this. Here is our roadmap for today's explainer. 1. The invisible messengers. 2. Anatomy of a wave. 3. Light in empty space. 4. Interacting with matter. And 5. Encoding the digital world. Let's get right into it.
Section 1. The invisible messengers. What exactly is traveling through space?
I really want you to think about this for a second. You hold a flat piece of glass and metal in your hand, you tap the screen, and boom, almost instantly, a friend all the way across the city gets your message. Or you click a thumbnail and a high-definition video just starts playing right out of thin air. There's no physical wire attached to your phone, right? There's no tiny tube carrying a piece of paper. So what exactly is moving through the space between you and the network? This brings us to the essential question of this unit. How do waves carry energy and information? This is the incredible scientific mystery we're about to solve together. Because to understand how a text message basically flies through the air, we have to look away from the computer chips and the glowing screens and look deeply at the fundamental physics of waves. We need to figure out how something totally invisible can have such a very real, measurable impact on our physical world.
Moving on to Section 2, Anatomy of a Wave, Concrete to Abstract.
Before we can fully grasp the complex digital devices sitting in our pockets, we really need to step back and look at the physical, mathematical model of a simple repeating wave. This lesson actually proceeds from very concrete observations, stuff you can physically see and touch, to much more abstract concepts. So let's start with a foundational definition. A wave is a repeating pattern that transfers energy from one place to another. So the crucial point here is that waves carry energy, not matter. Think about doing the wave at a football game. You might accidentally spill your nachos, but you and the rest of the matter mostly just stand up and sit back down in the exact same spot, right? But the wave itself, the energy in that pattern, travels all the way around the arena. Or picture dropping a pebble into a calm pond. The water molecules mostly just bob up and down in place, but that ripple of energy travels continuously outward to the edge.
Now, what's really interesting about this slide is how we can take that repeating pattern and actually measure it. In science, we always want to describe things both qualitatively and quantitatively. We do this by looking at three main properties. First up is wavelength, which is literally the physical distance from the peak of one wave to the peak of the next. Second is frequency, meaning how many of those wave peaks pass a certain point in a given amount of time. And third is amplitude, which is essentially the height of the wave from its resting position. These three properties, they are the universal vocabulary we use to describe every single wave in the universe.
Now, out of those three properties, the relationship between amplitude and energy is absolutely crucial. It's one of the most important things you need to take away from this. The amplitude of a simple wave is directly related to the amount of energy it carries. Think about water waves at the beach for a second. A wave with a tiny amplitude, just a little ripple, doesn't really have much energy. It just lightly taps your ankles. But a wave with a massive amplitude, like a towering tsunami, that carries a devastating amount of energy. In physical science, using mathematical representations to link a wave's amplitude directly to its energy is a major foundational standard for this grade level.
Which brings us to Section 3, Light and Empty Space. Journey to the vacuum.
Okay, so that covers the basics of physical waves like water or sound. But now we need to transition into how waves behave entirely differently depending on their exact type. There's kind of this grand divide in the world of waves. We're taking a journey from simple concrete water ripples right up into the vast empty vacuum of space. Because the waves connecting your phone to the internet, yeah, they aren't made of water or sound. On the left here, we have mechanical waves. These absolutely require a physical medium to travel through. Sound waves need air, water, or a solid to actually vibrate. Without matter, mechanical waves just stop dead in their tracks. But on the right, we have electromagnetic radiation, which includes things like visible light. These waves can travel through completely empty space. And honestly, this is a massive revelation. Because light can travel all the way from the sun through the vacuum of space to reach Earth, we know definitively that light cannot be a matter wave like sound. It plays by an entirely different set of rules.
Section 4. Interacting with matter. Crashing into reality.
So we know electromagnetic waves travel perfectly well through empty space, but our world is, well, full of physical stuff. So we need to explore what happens when these invisible electromagnetic waves suddenly crash into the physical world and interact with different materials. When these waves, like light, shine on an object, three distinct things can happen. Number one, it can be reflected. This means the wave simply bounces off the surface, which is exactly how your bathroom mirror works. Number two, it can be absorbed, meaning the object literally takes in the wave's energy. This is why a black shirt feels so hot on a sunny day. Or number three, it can be transmitted, meaning the wave passes straight through the material. And a really key concept here is that light travels in perfectly straight lines until it hits different transparent materials, like moving from air into a glass of water, where the path of the light actually bends. This bending is called refraction, and it's exactly how the lenses in your glasses or microscopes work.
Let's move to Section 5 and see how this all builds together. Encoding the digital world. Science to technology.
All right, we've established what a wave is, we know electromagnetic waves can travel through empty space, and we know exactly how they interact with matter. Now we arrive at the ultimate problem-solution engineering arc of modern communications. How do we take these invisible waves and actually use them to send a text message? Let's look at this as a worked example comparing the past to the present. Back in the day, we used analog signals. Think of an old radio broadcast or a scratchy vinyl record. The wave shape continuously changes to mimic the information. It works, sure, but it's super prone to static and interference. Today, however, we use digitized signals. According to the scientific and technical information we study in this lesson, using digital wave pulses is a vastly more reliable way to encode and transmit information. Instead of a continuous messy wave, we send information as sharp, crystal-clear wave pulses. It's essentially sending rapid-fire on and off signals, a 1 or a 0. This digital encoding is incredibly robust and highly resistant to errors.
And this brilliantly illustrates the application and transfer task of this lesson, taking our scientific knowledge and transferring it into everyday engineering marvels. Consider fiber optic cables. These use our knowledge of light transmission and reflection to shoot incredibly fast pulses of light through tiny glass tubes across entire oceans. Next, look at Wi-Fi devices. They utilize radio waves, which are just another form of electromagnetic radiation, sending digitized wave pulses right through the walls of your house. And finally, your devices take those stored binary patterns of invisible pulses and magically convert them back into something you can actually experience, the sound pumping out of your speaker or the texture reading on a screen. We are quite literally harnessing the fundamental properties of the universe just to stream cat videos. It's wild.
So I want to leave you with a final thought to ponder. We've decoded the science of how your devices communicate using amplitude, frequency, and digitized pulses of electromagnetic radiation. You now know that the room you are sitting in right now is completely filled with these invisible messengers carrying data, music, and videos all around you. If the invisible electromagnetic waves around you right now were suddenly made visible, what would your world look like? Honestly, it would be a breathtaking, chaotic ocean of pulsing, intersecting energy. You might never look at your smartphone or the empty air around it the exact same way ever again. Thanks for exploring this invisible world with me. Keep wondering, keep learning, and I'll catch you in the next explainer.